Okay, so we're going to begin with the proof of Euler's theorem. So let me give you a recap of last time. So some things that we discussed last time. So associated to a polyhedron, P, we can get a graph, G, just by considering the vertices and edges of the polyhedron. So for the tetrahedron, this looks like, we can draw this like this. Sorry, that's not pretty. Okay. And so this graph is called the one skeleton of the polyhedron. So Euler's, let me remind you what Euler's theorem says. For P, a polyhedron, if let me say with one skeleton G, denoted G, so if G is connected and any let me try to save space, any polygonal loop not necessarily edges. I'm going to comment on this in a second. Separates P into two pieces. So then the number of vertices minus the number of edges plus the number of faces of P is exactly 2. Right, so this remark here will make more sense once you see the proof. But so let me just draw a picture. Well, yeah, so a polygonal path might look something like this. I mean, it's composed of some straight line segments, but it doesn't have to be made up of edges. Okay, the reason why, yeah, so there's the reason why we want this assumption will make sense once we see the proof. Okay, let me mention a couple more things that we discussed last time. So every graph G has a tree that contains every vertex. So we didn't prove this last time. This is on homework 1. And then the last thing I want to mention now is for a tree, the number of vertices minus the number of edges is always 1. Okay, so now let's prove Euler's theorem. Since I have the theorem here, let me keep it on the screen. Okay. All right, so here's the theorem. So the proof is going to have 2 steps. So step 1 is to, well, okay, I've called this step the dual graph, dual. And you'll see what that means in a second. So, all right, so we're given this polyhedron and it has these 2 properties, and our ultimate goal is to compute v minus e plus f for the polyhedron and show that it's 2. So we need to get a bit of a handle on the polyhedron, and we're going to do that using graphs. So first, choose T in G that contains every vertex. And we're going to define a dual graph which will be denoted G prime. So its vertices will be in one-to-one correspondence with faces of P, and edges to vertices are connected by an edge when the corresponding faces meet along an edge not in the maximal tree. So let me draw a picture to show you what is going on here. So we have our polyhedron P, and we've chosen some maximal tree in the one skeleton. So it meets every vertex. It's a tree. So something like this. And we're going to define a dual tree where whose vertices correspond to the faces, and then you connect to if those faces meet along an edge not in the dual tree. So, well, it's a little bit hard to see in this picture here. So let me draw this differently. So here's the one skeleton. And this will give you, yeah, so, okay, so let's see. So, so we chose a tree here. Let me choose the same one that's in my notes. Let's choose this one. And then, oh, okay, so then this G, so okay, so that's T, and then we define G prime. This dual graph, it has vertices for every face of the polyhedron. And the polyhedron has 6 faces. There's one sort of on the outside here. And then you connect 2 of these vertices when the corresponding faces share an edge that's not in the dual tree, or that's not in the tree T. So we get, this is G prime. Okay, so this is the dual graph, G prime. And the first thing we want to prove about it, the main thing, is that G prime is a tree. So it's not just any old graph, and as you see in this picture, G prime is a tree. And so the claim is that this is always true. Of course, with the working assumptions of Euler's theorem. Okay, so let's prove this. So suppose for a contradiction, that G prime is not a tree. So by our characterization of trees last time, we know that this means that there exists some non-backtracking loop let's call it gamma in G prime, in this G prime. Right, and well, G prime is a graph, so this loop, well, we're thinking about G prime as sitting inside of P, and so this gamma is a polygonal loop in G, and so by assumption, polygonal loop, gamma separates P into 2 pieces. So by assumption, gamma separates P. But this is a problem. So here's the picture. So we have this polygonal loop, gamma. Maybe I should have drawn it in a different color. So this gamma, and so remember that, well, this is gamma inside of G prime, and the edges of G prime are dual to edges of P. Let me not use green, let me use blue. And then, right, so the picture is something like this. So you have to remember that the vertices of gamma prime correspond to faces of P. And so that's these polygons that I'm drawing here. And the edges of gamma prime come when 2 of these polygons meet along an edge of P, which is not in T. So yes. Right, so here's the point. right, so the existence, so this statement, this contradicts the fact that T is connected contains every vertex of P and is disjoint from, well, G prime and hence also gamma. So this gamma separates P into two pieces, and each of those pieces contains some vertices. So I mean, we can see that in this picture. So there are some vertices here on one side of gamma, and then there are some other vertices on the other side. But T is supposed to be a connected graph that contains all the vertices. So these two facts, the fact that gamma separates P into these two pieces, and the fact that T is connected, doesn't meet gamma, and contains all the vertices, these are in contradiction. Okay, so that's the contradiction that we're aiming for. And so then we conclude, so therefore, G prime is a tree. Okay, so this is the first step in the proof. So what we've done so far is we've constructed, chose a maximal tree, we constructed this dual graph, and we've shown that the dual graph is always a tree. Okay, so now comes the step 2, which is the final step. And step 2 is just to compute. So we want to know this quantity, vertices minus edges plus faces of P. And well, given this decomposition of with the tree and the dual tree, we can rewrite this. So the vertices of P, well, those are the vertices of the tree. The tree contains every vertex. And now the edges of P, well, there's two sorts of edges. There's the edges that come in T, and then there are the edges that come from edges of the dual tree. So maybe this picture is the right picture. So you have edges in T, and then you have edges that correspond to edges in the dual tree, as you see here. So each edge in the graph, or in the of the polyhedron P, meets exactly one edge. Well, it's either in the maximal or the tree T, or it's in this dual, or it meets the dual tree G prime. Okay, so then the total number of edges is this sum. And the number of faces is, well, remember that the vertices of the dual tree are in bijection with the faces of the polyhedron. Okay, so we have this equality. And we rewrite this like this. And if you are keeping up at home, then you should be salivating at this point because we are almost there. So now we have this expression, T and G prime, this should be a G prime. These are both trees. And we know that this value of the Euler number for a tree is always 1. So this is 1, and this is 1. And so the sum is 2, as as desired. Okay, so this is the proof of the theorem. It's not particularly complicated, but it's rather clever to define this dual graph in this way and to observe that it's always a tree. But once you know that, then the computation v minus e plus f is straightforward. Okay, let me make a little remark now before moving on. So Euler's theorem, it says if you have a polyhedron that satisfies some properties, then its Euler number is 2. So the remark is, well, for all the examples we've seen, although we haven't seen that many, yeah, so we've seen with Euler number equal to 2, P is topologically just S2. Well, okay, so this topologically S2 is something we're going to make precise in just a second, but okay, hopefully it's clear what it means. I mean, the tetrahedron, it basically looks like the two-sphere. And the question is this always the case? Right. There's, I guess, two different questions. This is maybe a little ambiguous. What is this? So really what I mean is, well, this is a fine question, but I guess it's slightly different than what the question, sorry, one second. Yeah, this isn't quite the question I want to ask. This is a reasonable question. Let me, really what I want to ask is if you have a polyhedron satisfying the assumptions of Euler's theorem, P is topologically S2. And is this always the case? So of course, the things satisfying the assumptions of Euler's theorem have Euler characteristic 2. But it's not clear if the converse of that is true, although we'll discuss that eventually. Okay, so this was just meant to be a side remark, and it seems that I've potentially made it confusing. So let me just move on now. Okay, so now comes a new topic, which will connect back to Euler's theorem. So this is the notion of topological equivalence. So let's start with the definition. So X and Y are subsets of Rn, are said to be topologically equivalent if there exists a continuous bijection from x to y with continuous inverse. And in this case, we'll write x topologically equivalent to y like this. So ultimately, eventually, we'll need to give a rigorous definition of what continuous means. But for now, let me not go down that road. So intuitively, f continuous means that if x1 and x2 in the domain are close, then f of x1 and f of x2 in the codomain are close. And well, yeah, if x and y are subsets of Rn, then I guess you have some idea of what close means, since Rn has a distance. Eventually, we'll want to make this definition completely general for x and y topological spaces. But that's getting a bit ahead of where we are right now. Well, okay, so let's just state it like this. Okay, so I want to just give some examples and non-examples to give you some sense of what this notion of topological equivalence is. So let me start with a non-example. If you want to understand the definition, it's good to understand when it goes wrong. So let's start there. So let's take x to be an interval like this. So I guess I haven't used this notations. So by this I mean points in the real line, which are between 0 and 1, including 0, not including 1. And let's take y to be the circle. The unit circle. So this is points in R2, x, y, x squared plus y squared is 1. Sorry, this is too small a space, but okay. So there's a continuous bijection from x to y given by sending x to cosine 2 pi x sine 2 pi x. Okay, so it sends this interval into the circle in the following way. So 0 goes to, well, to the point 1 comma 0, and it wraps this interval around the circle exactly once. And as you approach this endpoint, the value approaches 1 comma 0. So this map is continuous, is a bijection, but here f inverse is not continuous, which, well, you can see because, well, here you have, you know, points just above or just below the positive x-axis on the circle go to different places. Some go over here and some go over here, so they're not close. Okay. And so, well, I guess eventually we'll see that these two examples, x and y, are not topologically equivalent. That doesn't follow from this discussion, but well, yeah, well, okay, fine. How about some examples? So the tetrahedron is topologically equivalent to the two-sphere. So this is x, y, z in R2, unit, or in R3, distance 1 to the origin, analogous to the unit circle. And well, so right. So if you're claiming that two spaces are topologically equivalent, then to prove that, you have to come up with a continuous bijection from one to the other with a continuous inverse. And so let me just, I'm not going to do this rigorously now, but let me, so the proof that these are topologically equivalent, or, well, one way to do it is by radial projection. This is a useful map to know about. So we have the two-sphere here in R3, and then let's position the tetrahedron inside. And inside of there, let's have the origin. And so the radial projection map, well, given a point on the tetrahedron, you draw a ray from the origin to x, and that will hit the sphere at a unique point, which we'll call f of x. So this is the sphere. I like to draw it like this. So this is, well, okay, so r of x, let me call it f, is x over norm x. You just normalize x and to get a point on the sphere. Okay, and well, okay, so this is a continuous bijection. The inverse is also continuous, which I'll let you convince yourself of. Let's do another example. Just to get familiar with this notion of topological equivalence, at least intuitively. So let's take S2 as above and remove a single point, the North Pole, 0, 0, 1. And I claim this is topologically equivalent to R2. And one way to see this is with what's called stereographic projection. Which maybe you've seen if you've taken complex analysis, or maybe you've seen some other place. So let me tell you how this works. So I'm going to define a map from the two-sphere. I'm going to define a map like this, F. So here's the two-sphere, and here's the North Pole. And here's R2. In the XY plane. And the way the map is going to work is, so, okay, you give me a point on the sphere, X, and let's draw a line or a ray from the North Pole to X. That's going to hit this plane at a unique point, which we'll call f of X. So for example, if the point you start with is in the lower hemisphere, then this projection is going to land in the unit circle in R2. This projection map fixes any point on the unit circle, sends the unit circle, the unit circle here to itself, and then it sends points in the upper hemisphere outside of the unit circle in R2. And as you get closer and closer here, then the projection, or this line, moves further and further towards infinity in R2. Okay, so I think there's a homework problem where I'm going to ask you to write down a formula for this, which maybe is useful for convincing yourself that it's a continuous map and it's a bijection and the inverse is continuous. Okay, another example related to Euler's theorem, and this, I guess, is the last example. I'm going to state it as a theorem. So let P be a polyhedron satisfying the assumptions of Euler's theorem. So, okay, the one skeleton should be connected, and every polygonal loop separates. So then P is topologically equivalent to S2. So this is meant to answer the question that I raised here that I wasn't stating, well, that I didn't state so clearly. But right, so as it turns out that any polyhedron satisfying the conditions of Euler's theorem is topologically S2. So the way you should think about this is, well, this theorem gives you a characterization of S2. It tells you what are the key properties that make the two-sphere the two-sphere, as compared to any other polyhedron, like the surface of a donut, like the torus polyhedron. So this is a nice result. So I want to explain the idea of the proof. Because it's a very pretty idea. So we're going to use the proof of Euler's theorem in the following way. So there we found complementary trees, T and G prime in P. And what we're going to do is thicken these two disks. So let me draw a picture. So let's take P, the tetrahedron, and we're choosing a maximal tree. Maybe something like this. And then we have this dual tree. these pictures are always not so satisfying like this. Let me draw it differently. Let me just draw the graph. Let me try to draw it planar, in a planar way, rather. So here's the one skeleton, and we have T and the dual tree in green, G prime, which is like this. And what we're going to do is thicken these. So you can just sort of, well, take a little neighborhood of each of these trees and slowly, well, I mean, you can imagine doing this, you know, well, making the neighborhoods larger and larger with some parameter time, and then eventually they're going to meet. So we're thickening them to disks, and until they meet. And when they meet, well, so neither of these pictures is completely satisfactory, because here you can't see the outside. There's a face missing, and plus it's just a total mess. But yeah, so okay, so the claim is then you get a description of P as a union of two disks glued along their boundary, the boundary circle. So, okay, so actually for this, I have a prop that hopefully will illustrate. So, okay, so we have these complementary graphs. So the way these two, okay, so this is the picture to keep in mind. So we have these two complementary graphs. Let me see if I can show you. So here's the one graph, and then the other graph is here. And if you thicken these two graphs, then what's happening is you're getting something like the two patches on a tennis ball. So you thicken this black, you get this little disc. Wow, it's really hard to coordinate. Okay, so you get these two discs, and they meet exactly on a circle, and that circle is, wow, I'm really bad with left and right and mirror imaging. Anyway, okay, hopefully you get the point. You have, this is the picture that to have in mind. You have, when you thicken T and G prime, then you get these two disks, and they're glued together along the boundary, a boundary circle. And well, if you this is a description of S2. I mean, S2 is, well, it's two disks. You have the top hemisphere and the bottom hemisphere, which are glued along along a circle. So topologically, that's what you get. Okay, so great. So let's see. That's all I wanted to say for today. Next time, so I'm just looking to see what is coming next. Yeah, next time we'll talk more about topological equivalence and about topological spaces. Okay, so see you then.